Hello everyone. Today we are going to be looking at the last section in this chapter on linear equations in linear algebra. It is titled The Matrix of Linear Transformations. The topics which I'll cover are the following. We're going to first do a recap of matrix equations and transformations, then matrix transformations and linear transformations, and then we'll study the matrix of linear transformations and answer the most important thing, the existence and uniqueness questions related to these matrix of linear transformations. Okay, so let's begin with the recap. Now, the first thing I'm going to say is, what is the matrix equation? I hope you guys know by now. It's a matrix equation. It's given by Ax equals B, where A is a matrix of size m by n, X is a vector in Rn, and B is a vector in Rn. It is just another way of finding all vectors. So when we solve this matrix equation, so solving a matrix equation is like finding all vectors in Rm which are transformed to vectors in Rm under the action of the multiplication of A. Remember, where is this A? We did that in a last session on the introduction to linear transformations, that when you have a vector, so when A acts on X, so that means this matrix equation can be thought of an action of the matrix on a vector X. Here, this vector is in Rn, and when you multiply this vector X by A, it takes you to another vector B, which is joined by Ax. Now, this transformation, which is brought about by matrix multiplication, is called a matrix transformation, which we're going to talk about in a minute. So what we're seeing is the relation between a vector X and a vector Rn. This relationship is reflecting a function from one set of vectors to another set of vectors. And remember, a transformation is nothing but a rule which assigns a vector in Rn here, to a vector in Rn. So let's formally define it. A transformation, remember, is either a function or a mapping. But in the linear algebra world, a transformation is used as the terminology for functions or mapping. So a transformation T from an n-dimensional Rn to Rm is a rule which will assign each vector in X in Rn a vector Tx in Rm. So basically we have a T from Rn to Rm. I'm saying a word transformation here, okay? So this is a very general definition. Rn is called the domain of T and Rm is called the codomain of T. Okay, now for any vector x in Rn, the vector Tx in Rm is called the image of X under the action of T, which is defined by Tx, under the action of T at this point. Now, the set of all the images Tx is called the range of T. Let's look at a graph. So T is a transformation or a rule which assigns a vector x in Rn a vector Tx in Rn. So remember, the green part goes to the green part. That means the green part in the codomain is called the range because every element here in the green part has an element associated with it in Rn. That's what it is. Okay? Now, what's a matrix transformation now? A matrix transformation is a transformation defined by Rn into Rn, which is defined by Tx equals Ax, where A is a matrix of size m by n and x is a vector in Rn. In other words, when we are going from one vector to another vector, so here we're going from Rn to Rm, we have this transformation T. Now this T is defined by the multiplication of the matrix A to the vector x in Rn. Okay? Now, for simplicity, we're going to denote the matrix transformation by x into Ax. And as I've also repeatedly said earlier, I will prefer to use the full definition than going by this notation. This makes it much more clearer every time what I'm doing. Okay, some observations. For each x in Rn, Tx is computed as a matrix product of the matrix A with the vector x. Now the domain of T is Rn, and this domain, the n is related to exactly the number of columns of the matrix A, and the m in the codomain of part of the transformation is related to the number of entries in every column. And the range of T, remember what we said? We said Tx equals Ax, and Ax is a vector in Rn. And this matrix equation, Ax equals B, can be written as a vector equation, A1 x1 plus dot dot dot, An xn equals B. That means this range of T is the set of all linear combinations of the columns of A, as every image Tx is of the form Ax. Okay, now let's go to the definition of linear transformation. A transformation or a mapping is linear if T preserves the vector addition, that is the transformation, so this linear transformation, it preserves vector addition. When T acts on u plus v, it is equals tu plus tv for all u and v in the domain of T. And T preserves the scalar multiplication, that is T of c times u is c times du. A very important part, which simply says that the linear transformation preserves, the first one says vector addition, and the second one says it preserves scalar multiplication. Okay? Now, there's a relationship between a linear transformation and matrix transformations. So let's go back, study that too. We know that every matrix transformation is a linear transformation. And what is a matrix transformation? Which we have already said, T is defined by this. Now let's look at this one. We say every linear matrix transformation is a linear transformation. Oh, okay. Let's look at it. What's a matrix transformation? T is a mapping from Rn to Rm defined by Tx equals Ax. And this says every matrix transformation is a linear transformation. Okay, so to prove that it's a linear transformation, you can say let x and y be vectors or be elements of Rn and C and D be scalars. Then T of Cx plus dy equals, according to the definition, A of Cx plus dy. Okay. Now, A is a matrix multiplied, C times x is a vector, and D times y is a vector. When you add them, it's a vector. Because of the matrix properties, we can write this as A times Cx plus A times dy. Now remember, C is a scalar, and scalar can be again taken out by the virtue of the properties of matrices. So it's C times Ax plus D times Ay. Now what is Ax? Is nothing but C times Tx plus d times dy. And we have basically proved that every matrix transformation is a linear transformation, and because of the properties of matrices. Okay, very important fact, if T is a linear transformation, then T maps the 0 element to the 0 element. And for every vector u and v in the domain of T, T times Cu plus dv is Ctu plus d times dv. And that's what helped us to prove that every matrix transformation is a linear transformation. Now, going backwards, be careful. It's like a one-way direction. To go backwards, we are going to talk about a very important theorem here. Now, what will make a linear transformation a matrix transformation? We will do that in a few minutes, but let's start with an example of what we have talked about so far. Okay, if T is a transformation which maps E1 into Y1 and E2 into Y2, where E1 and E2 are the columns of the corresponding identity matrix of I2, and Y1 and Y2 are elements of R3. The question is, find a formula for the image of an arbitrary x in R2. In other words, if T is a linear transformation, so I have an matrix, T goes from R2 to R3, I pick up any x here in R2. So when T acts upon it, okay, we like to know what does dx looks like. An arbitrary x, what would be the image of an arbitrary x in R2? So we'd like to know what is that relationship. Okay, what are we given? We start from what's given. We said T maps E1 into Y1 and E2 into Y2. That means T of E1, or when T acts on the first column of the identity matrix, I get the vector -2, 1, and 9. And when T acts on the second column of the identity matrix, 0 and 1, remember identity matrix I2? 1, 0, 0, 1. That's what it means, E1 and E2. That's by a convention we follow E1 to be 1, 0 in the math world and E2 to be 0, 1. So T of 0, 1 is 7, 0, minus 1. Okay, now we want to know what happens when x is there. X is an arbitrary element. Okay. So, T of x. Now, if x is an element of R2, that means x will have two values in the two rows, x1 and x2. They're any values, in the first row and the second row, because it's an element of R2. So then T acts on x1 and x2. Now, what is x1 and x2? You can write this as x1, 0 plus 0, x2. Now, clearly you can take the x1 out, a scalar multiple, 1 and 0, and x2 will be 0, 1. Now, 1, 0, remember, is nothing but the vector E1. 0, 1 is nothing but the vector E2. Now, from here, when T acts on this linear combination, and T is a linear transformation, as T is a linear transformation, what happens? I can actually write T of x1 E1 plus T of x2 E2. Remember, T preserves vector addition. Okay, now let's look at individual T's here. So T when acts on x1 E1. It also preserves scalar multiples. So that means you can take the x1 out and you have T of E1 and x2 T of E2. Once again, T is a linear transformation. Now, look at this one. Guys, this is a vector equation where the vectors are T of E1 and T of E2. And x1 and x2 is written as together in a vector form. That's an element x. So, I have an arbitrary element x. And when I write this one, what do I notice? An arbitrary element x is basically can be written as, when T acts on an arbitrary element x, we find that it can be written as a matrix equation where the matrix is nothing but the action of T on the individual columns of the identity matrix. And we are given what T of E1 does. T of E1 is the vector minus 2, 1, and 9. T of E2 is a vector 7, 0, minus 1. So this is the matrix A, and this is the vector X. So what we have got is that if we are given an arbitrary element X, then T, when acts on this arbitrary element X, it basically gives us a matrix equation where the matrix is nothing but composed of the action of T. This is what I'm talking about, guys. Action of T on the identity columns. Okay, and that's where the very powerful theorem comes in. Theorem number 10. What it says is, if T is a linear transformation from Rn to Rm, that means we are working, if I have a linear transformation from a one-dimensional space to another dimensional space, then that will give us a unique matrix A, such that Tx is equal to Ax for every x in Rn, and this matrix A is formed by the action of T on the columns of the identity matrix. Oh, forgot this little square bracket. Now this matrix A, guys, is a unique matrix, and that is what shows that every linear transformation from a n-dimensional space to an m-dimensional space makes this linear transformation a matrix transformation. Remember that. Remember we said that every matrix transformation is a linear transformation. And we were asking the question, what linear transformation will make it to be a matrix transformation? And here is the key. A linear transformation which goes from an n-dimensional space to an m-dimensional space. And this matrix A, which is formed because of this relationship, is called the standard matrix for the linear transformation T, and this is a unique matrix, very important. Okay, let's look at some observations. That every matrix transformation is a linear transformation. We said that. This is a very important, that every linear transformation from an n-dimensional space to an m-dimensional can be viewed as a matrix transformation, and we get this Tx as Ax, and which is formed by T of E1 dot dot dot. It depends upon how many columns will be the columns of the dimensional space of the domain of T, which is n, so that means that many columns, and the vector x1 dot 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 xn. Okay, now the term linear transformation focuses on the property of mappings, because transformation is a mapping, whereas matrix transformation tells us how this mapping can be implemented. Okay, we've done a lot of theory, guys. Examples time. Let's do it. Now, show that T is a linear transformation by finding a matrix which implements that mapping. Okay, so this is a linear transformation. T of x1, x2 goes to an element 2x2 minus 3x1, x1 minus 4x2, 0, and x2. So when I look at this one, this gives me the clue that T, how many elements are here? x1 and x2 are not vectors, but entries in a vectors, are 2. And how many entries in this vector on the right hand side of the equal sign? 1, 2, 3, 4. That means T is a mapping from R squared to R4. Okay, now we want to prove that something is a linear transformation, and we are given that relationship. You just have to find the standard matrix corresponding to it, and voila, we have a linear transformation. That's how you show that T is a linear transformation. A much more easy way here. So we can write T of x1, x2 T of x1, x2. That means this is given by the definition. Now, from here to here, guys, we have done lots and lots of practice. So this is basically writing this as a vector, and then we can write this as a matrix times a vector, and x2, x1. So here x2 comes here. So you've got to be very careful how it is written. So everything else writes x1 first. This one's x1. So I'm having x1 to be first. So I have to be very careful of how I write. This is -3 and then 2. 1, -4, 0 and 0 and 2. You got to be very careful of how you write this one. And this is a 4×2 matrix, and that's the standard matrix A. So if I give you say, prove this is a linear transformation, and I give you that relationship, if you can show the standard matrix, you are done. Okay. Here, we're going to add complexity to the problems here. We say let T be a linear transformation from R² to R3 such that this is how it is defined. So clearly when I look at this, I would like to know which space I'm going to. So T is the vector from x1, x2, R² going to where? 1, 2, 3, R3. That's where it goes. That means the standard matrix corresponding to this would be a matrix of size 3×2. Okay. So that's when you are given. So make sure that you can make the connections in seconds. It takes time, but it will in a few practices it will be very easy for you. Now the question is, find the vector x such that Tx equals -1, 4, and 9. Okay, what does this mean? Let's draw little maps. T is the element from R² to R3. I want to find an x here such that when T acts on it via this relationship, and T goes to a vector which is given by -1, 4, and 9. What does that mean? It means that we have to solve Tx equals b. I want to find T, that means Tx, remember, which is Ax, equals b. In other words, we are doing what? We are doing section 1, 2, applying the row reduction algorithm to find the x. That's what you're basically doing. Remember, it's all different types. We are basically going every time back to applying the row reduction algorithm. Different ways of asking the same question, but the base is still the same. Okay, so the question is, find this x such that Tx equals -1, 4, and 9, which basically amounts to saying that the corresponding matrix equation is consistent. That's what it simply means, that this matrix equation is consistent. If you say find the x, that's when the way the question is framed, guys. Okay, so that's what I just talked about, and this is how it is written. And now if I want to find this x, what do? I write the augment matrix. When I write the augment matrix, after that, apply the row reduction algorithm. Okay, that's the next slide. Okay, here we are. We have this augment matrix. Now, you should be a pro by this time, guys, to do all this row reduction algorithm. We have been doing it so many times. And if I want to row reduce, that means if you say find the x, what I basically mean is my coefficient matrix should have the columns of the identity matrix. That's what it means. And the last column will give me the answer. The first one will give the x1. Second one, the second row element will give me the x2 variable value. So the image of this x under T, x equals 5, 3. So basically it means the value 5 and 3 when acted upon by T gives me the value -1, 4, and 9. That means this is not going to give me a value. It basically takes this vector under the linear transformation, takes it to this vector. Okay, now we're going to once again go back and do a little recap of functions, special kinds of functions, guys. Okay, let's go back to that scenario. Now, a function, we remember, is a rule which assigns to each element of a set A a unique element of set B. The whole set A is the domain, and the whole set B is called the codomain of the function f. The range means all those elements in the set B that have an element, say, x in A. Now, those were just a repetition of what we have been talking about. The very important thing is for us is type of function. A function is 1, 1. A function is onto. So a function is said to be on 1, 1. If f of A equals f of B, then A is equal to B for every A and B in the set A. Okay, this is like the proper pedantic definition. I'm going to give you a very simple graph. It means if my function is 1 to 1, that means if 1 and 2 are there, they are related to, say, a star and a little smiley face, guys. I hope I can make it. Oh, kind of. Okay, let's try to make it one more time. Okay, you know I love smiley faces. Okay, here's my smiley face. Little smile. Kind of. Okay, we'll just let it go. Okay, so here's my set. 1 to 1 means 1 goes to star and 2 goes to smiley, and that's it. You cannot have more than that. But if it is a function, I can have, if it is 1 to 1, I can have another one. Say I have a square. Okay, this is also a 1 to 1 function because if there's 2 elements in the domain, then it will only go to unique elements in the codomain. That's the meaning of 1 to 1. On the other hand, this function, which I have just created, this is 1 to 1, but not onto. What does onto mean? Onto means every element in the set B should have an image in A. Okay, so here's the scenario. So we have 1, 2, and if I had these 3 elements, my star and my square, and my little smiley face. That came out well, guys. So it means if it is onto, 1 goes to star, 2 goes to smiley, but this little square also needs to go somewhere. So this it cannot go to 1 and 2. Remember that, because it won't become a function. So we can have, say, the number 3 going to the square. That's onto. Remember, the top one wasn't onto, but the bottom one is onto. Okay. Another example of an onto is this. So, okay, I need to find some space. So here's another way. I have 2 sets. I'm going to make my life easy. So I have only elements, say, K and L. And I have 3 elements here. 1, 2, and 3. Okay, as it is onto, 2 goes to K, 1 goes to L, but remember it's a function, it has to, 3 has to, so 3 can also go to K, or 3 can go to L, doesn't matter. But this also is an onto function because every element of B has somewhere to go to in A. And at the same time, it is a function. Okay, now, let's look at what is the meaning of onto in terms of linear transformations. We say a mapping, not linear, but let's say in terms of transformations, a mapping T is said to be onto if each B in Rm is the image of at least one X in Rm. In other words, this, guys, these two we are talking about. Okay, now what does it mean in terms of when you're having it's a transformation and linear transformation? So if we say T is onto Rm, when the range of T is all of the codomain of Rm, or it means there is a solution of this matrix Tx equal to B. Now here we are talking of a matrix transformations, guys. Here Tx is equal to B. Okay, If it is, that's a matrix equation, that means there exists at least one solution of Tx equal to B. So T mapping Rn onto Rm is an existence question. The mapping T will not be onto when there is some B in Rm for which this equation Tx equal to B has no solution. Okay, let's look. And when I'm talking of this Tx equals to B and thing, I'm trying to make it into things which we are more comfortable with. I'm comfortable with, hey, if it is a matrix transformation or if it's a linear transformation, so I'm going in those directions over here, guys. But this can also become much more general too. So be very careful of how we use it here. Okay, but let's look at how the graph looks like. If I have a domain and it only goes to some part in the codomain, that means this is not onto. But onto will be a scenario where the range is the same as the codomain. So this means that the range of the transformation is nothing but the codomain of the transformation. Okay, let's look at what's the relationship of one-to-one and uniqueness in terms of equations. A mapping is said to be one-to-one if for every B in Rm, it is the image of at most one X in Rm. Or interpretation is T is one-to-one for if each B, this equation Tx equal to B has either a unique solution or none at all. So thus is TRN into, sorry guys, little mistake, some typo guys. Okay, so this means is T one-to-one, Rn into Rn, so like this. Is T R into under one-to-one a unique question? Okay. This mapping T will not be one-to-one when there will be some B in Rm, which is the image of more than one vector in Rn. Now, what does that mean? Remember, we had that nice little graph where we had a little smiley face going to 2 here, remember, and a 1 going to a star. And then, oh no, that was the K and L, I'm sorry, okay. And then we had 3, but we wanted to send 3 somewhere too. And this is not onto, I'm saying, so 3 ends up also going to a smiley face. So what's happening? I have 2 elements here, 3 and 2, going to the same element in the codomain here. Okay, this one is not one-to-one, but it is onto. So this is an example of not one-to-one, but onto. Okay, now graphically, I have another way of looking at it. When T is not one-to-one, you see there are 2 elements here which are going to the same elements in the 0 element here. So there are only 2 elements which every element of Rn is going to. But in this one, every element in Rn goes to a very different element in the Rn. Okay, so now we're going to look at some examples. It says determine if this linear transformation T R3 to R square is one-to-one and onto. And we're defining this T. Remember, if T is a linear transformation from a dimensional space to another dimensional space, that means it will have a unique matrix Tx equals Ax. Remember, we just did that theorem, which is basically made up of here 3, so it's going to be E2 and E3. That's the standard matrix. So this is my A, and the vector then X next to it. So first of all, we're going to write down the standard matrix. Now remember, T of E1, E2, and E3 is already given to us. So T of E1 is what? 1 and 3, 4 and -7, minus 5, and 4. Now, we have got the standard matrix, and we would like to know whether this linear transformation is 1-to-1 and onto. Which remember, we just talked about, if it is 1-to-1, that means the augment, the t of x, will have a unique solution or no solution. And if it is onto, that means it's going to have, let's look at this one. Let's go back over here. Onto means what? Onto means that there has to be at least one solution. That is the Tx equals b if you're looking in terms of our matrix transformations here. Okay, so we have written down the standard matrix. That's the whole, the way the formula goes. Just I've gone step by step for you guys. Now let's go back to the main question being asked. It says, to answer the question, we'll use the definition of 1, 1. Okay, 1 and 1 to 1 and onto, and how it is related to the solutions of the equation Tx equals b. We're going to look at the standard matrix. Simply row reduce it. Okay, and when we row reduce it, what do we get? Just a row echelon form. Okay, not the reduced row, just the row echelon form. When we do this one, what do we see? We get a pivot in every row. Now, if you remember, if there's a pivot in every row, by theorem 4, what does that mean? That the matrix is consistent. And that's what the definition is saying, that if your matrix is consistent, for every b, I have a solution. That means if there's a pivot in every row, thus T is onto. Now, in this matrix A, we had what? 1 and 0, and what was it? We have to figure out if it is 1, 1 and onto or not. 4, negative 19, negative 5, and 19. Okay, so since, look at this matrix, the standard matrix. It has two basic variables. As it has two basic variables, that means there's a presence of free variables, as well as it is consistent. That means there's going to be infinite solutions. If it has infinite solutions, what does it imply? That every b in Rm is the image of more than one vector in R3. That means it is not 1-to-1. Now, it takes us to two specific important theorems, theorem number 11 and 12. And remember, we will be basically applying the theorems. We are not going to be proving them. We will be using them here. So T is a transformation, linear transformation from Rn to Rm. We say T is 1-to-1 if and only if the homogeneous equation has only the trivial solution. Theorem 12 says, if T is a linear transformation from Rn to Rm and A is the standard matrix corresponding to it, then T will map Rn onto Rm if and only if the columns of A span Rm, or if there is a pivot in every row of the standard matrix. That's what it means. T is 1-to-1 if and only if the columns of A are linearly independent. What does that transcribe to? It simply means that every column is a pivot column. Okay. Let's do an example. It says Tx equals Ax for this matrix. That means this T is a matrix from a transformation from R3 to R3. And we would like to find whether this linear transformation, which has A as the standard matrix, is it 1, 1 and onto. As the things are already given to us, what are we going to do? We'll take this matrix A, row reduce it. So when we row reduce it, and what I normally try to do is write the row echelon form. And that's where I will start getting all the answers. Because I'm not looking for the final answer. I'm just looking at whether it is 1-to-1 and onto. Okay. So when we apply the row reduction algorithm and we get the row echelon form of it, what do we notice? That this one, let's talk about onto. That means there should be a pivot in every row. That's simply it means. Do we have a pivot in every row? No. That means it is not on 2. Because the theorem 4 of section 1.4 is not valid. Okay, is it 1-to-1? That means every column should be a pivot column. Only 2 columns are pivot columns. So, there are only 2 pivot columns. If only 2 pivot columns, what does that mean? It's not 1-to-1 because for it to be linear 1-to-1, that means every column has to be a pivot column. So, T is not 1-to-1. So, I have an example where neither it is on 2 nor it is 1-to-1. Okay? So, guys, here you will be practicing the following questions from the book. Oh, this is 1.9, guys. Sorry. This is 1.9, not 1.7. Okay, let me write this one down. 1.9. So many questions. Practice them. It will help you. And one more thing. Okay, guys. I just want to talk about certain things. This is a flow chart of all the things we have done so far. And I have posted it on detail. So notice, I'm just going to go over through this because this basically shows everything we have done and how they're all interrelated. So in this one, guys, the first thing you will see is the linear system. And let me just, okay, let me get this much more clear here. Okay, great. Increase this to say 70%. Oh, almost got everything. So let's change this to 60%. Okay, so there we get to see almost everything we need here. Yes, this is perfect. That's exactly what I need. Okay, so remember we started with a linear system. We say every linear system can be written as a matrix equation, which can be written as a vector equation. And when it is a vector equation, it means B is generated by the columns of A, or B is spanned by the columns of A. Okay. If it's a linear system, there are 2 scenarios. Either it is consistent or inconsistent. If it is consistent, 2 things can happen. Either a unique solution or infinite solutions. If it is infinite, that means at least one free variable. But if it is a unique solution, every variable is a basic variable. Okay. And if it is inconsistent, it can still have the presence of free variables. Remember, consistent means for a linear system, that means theorem 2 is valid. Very, very important of chapter 1. Now, let's go further. If it is basic variables and a unique solution and the linear system is consistent, that means the corresponding homogeneous equation has only the trivial solution. That means every column of that matrix A is linearly independent, or every column is a pivot column. And section 1.9 says if A is a m by n matrix, then the corresponding linear transformation is 1-to-1. That means every column of the standard matrix of this linear transformation is a pivot column. Now, let's go on the other side. If it has infinite solutions, the linear system, that means, and it has, definitely is going to have one free variable, which means that the corresponding homogeneous equation has a non-trivial solution. That means columns of the matrix A are linearly dependent. And if that means if for each B in Rm, this matrix equation has a solution, that means columns of A are spanning Rm. I'm talking of section 1.9. That means A has a pivot position in every row. If that's the scenario, that means the corresponding linear transformation is onto. Okay, guys? I would just like to remind you once more, you need to practice these problems. Thank you.